Listo. Bueno, buenas tardes. Um, the talk is going to be in English, so I'm going to present in English. It's a pleasure to me to introduce you Henrique N, who is going to talk us about updates on flow of geometric structures. Thank you, Enrique. Enrique.
All right. So good afternoon, everyone. It's always lovely to participate in the Córdoba seminar. I've participated in person before when visiting you guys, and it's always a great opportunity to integrate the things we've been doing, which are always sort of connected uh, geographically, but also mathematically. So this talk is called Updates on Flows of Geometric Structures, alluding to a paper with Daniel Fadel, Eric Lubeau, and Andres Moreno, called Flows of of Geometric Structures, which is now ahead of print, appearing on Krell's journal. This goes in tandem with, if you want, a specific example carried out in detail, which stems from a separate paper called "Flows of SU2 Structures," which dates back from, I think, June, with Uda Fauder, which can be seen as a sort of a deep exercise mobilizing the general theory formulated on the paper on general flows. So it's at the same time, when we announced the original work on sort of abstract theory of flows of geometric structures a few years ago, a year and a half ago, I think, maybe 2 years ago, and we submitted it to a journal, there was a fundamental mistake in a key step of the proof. So this is also an opportunity to tell the community that this result is indeed correct. It's now accepted, and it's also available online, soon to be an index publication. In fact, the mistake was found by the referee, so it's an interesting story. A mistake was found by a referee in the proof of epsilon regularity when we study the long-time behavior of the harmonic flow. And it is found to be, or its root is found to be at someone else's paper. So we're basing ourselves on an argument found in a different paper, which looks at flows of almost complex structures specifically, and a sort of harmonic flow of almost complex structures. And that paper contained a sort of mistake. So our job was, in fact, to fix the first paper in order to make our argument work. So it's the mistake is not really sort of our fault, but in order to fix it, we had to take responsibility over this. So it's also a service to the community that we were able, with the referee's collaboration, to fix it. If the referee was one of you, thank you so much, because it added a lot of value to the whole discussion. So what is this discussion about? Wait, I want this. Yes. So what's the business of geometric flows? Let's consider the sort of motivational benchmark for this, which is evolving the metric, right? So geometric flows in general address, flows of geometric structures in general address the issue of deforming along some prescribed deformation rule, some sort of evolution equation, a tensor corresponding to some particular reduction of the frame bundle. Think of geometric structures in that way. So the sort of most popular example is flow in the metric itself, corresponding to the reduction to the orthogonal group as structure group, trivial manifold, reduction from GL to orthogonal, sort of special orthogonal. So then the challenge is, when you want to evolve, let's say, the metric, it needs to evolve according to some tensorial rule, which depends only on G. And in that sense, those things are what we call invariant. They're tensorial quantities, right? We don't want to evolve in ways that depend on the choice of sort of local choices, right? We want to evolve by tensors. And we want to do so in a way that has any hope of existing in a long time, meaning particularly it has to exist in short time. So those are the desirable properties before one writes down any flow at all for the metric or the manifold. Those are the two things you would in principle expect. So what would be my possibilities for this, right? So and I'm also going to specialize to second order, right? We could consider flows of sort of arbitrarily high order. Uh, uh, Flows of first order wouldn't make any sense. There are no first order invariants of the metric, right? The Christoffel symbols are sort of not tensors, right? So if you were to find building blocks for flows, they would have to sort of start at second order. Let's limit the discussion to second order flows. And therefore, my second desirable property really is some version of parabolicity, right? That's what we basically have in mind. So what would be this, the invariance of G, meaning tensorial quantities depending on G? Well, they can all be extracted from the Riemann curvature. And if we're looking at further orders, then also its derivatives. And we can decompose, sort of formally, we can think of the curvature as giving information in terms of scalar, traces Ricci, and bio. So that if we wanted, however, bio is not a symmetric two tensor. So how would there's no way I could mobilize it to deform the metric as such, as a symmetric two tensor, right? So what we find is that indeed, if I want to deform the metric, the sort of only reasonable choices to second order are being a scalar curvature multiple of the metric itself plus the Ricci, right? And therefore, I can think of this as a general problem, as a two-parameter family of possible flows. In order to guarantee existence and other amenable properties, I have to specialize the choice of these degrees of freedom further and further. But the general perspective which we want to borrow from the discovery of these classical flows of the metric is the following. One wants to set up a flow as a way of finding a given geometric structure, for instance, a metric which is more special than the one you began with, meaning in particular that it's a solution to a particular PDE, right? So, or if it's a geometric structure of more general type, you want it to be special, meaning that it satisfies, for instance, some vanishing condition on some component of its torsion, right? So typically, the way we do this is someone guesses a really nice variational principle. So someone guesses some sort of action, some sort of a gradient flow type construction, showing that this has the promise of converging to a better structure than the one you started, and then carry out the variational analysis of this flow. But this begins from what one could call a sort of fetishistic position with regards to the original energy one decides to start with. Why would you start with the Dirichlet energy, or why would you start with just basically any other energy? In fact, the Dirichlet energy, as I'm going to try and convince you, is naturally justified as opposed to some other ones. So we can think of, for instance, the volume functional for G2 structures, right? We can think of, and then we find that its gradient flow can be expressed, for instance, as the Laplacian flow, or depending on how you look at it, it's the Laplacian coflow, depending on the sort of additional impositions you make on the variations you're adopting. These behave as the gradient flows of the volume flow, and they have the promise of converging, of stabilizing around torsion-free structures if you begin with a sufficiently special structure to begin with. right? That's drawing from the example, the seven-dimensional example of G2 structures. But this, so the kind of question we're trying to ask is, as opposed to trying to propose an original sort of fetishistic variational principle, which has a promise of converging, we kind of reverse the question and say, given that I can choose among, I mean, what are all possible flows I can choose from, right? Uh, and then such that a number of analytic properties are good analytic properties are satisfied. So it becomes an issue of knowing what are my tools available, what are my available building blocks for these flows, meaning what are my second order, in this case, tensorial quantities, depending only on my structure itself, which I can leverage into, in principle, setting up the general flow as a family, possibly a large number of parameters, and then I can choose the parameters. I can study the parameters so that I can cook flows with the analytic promises that are relevant to me at any given point, right? So this Ricci flow case is a prototype of the kind of, I mean, this explanation here of how you could discover, for instance, the flow by scalar curvature, or the Ricci flow, uh, thought of as starting from a general perspective where we locate the second order invariants, identify them as members of the family, and then make particular choices starting from there, depending on the spectral types of PDEs we want to solve. But one lesson to take here is that this is a fundamentally finite process. One cannot think of a third or a fourth second order invariant, right? That's the most general family that satisfy my desirable properties really is this two parameter family, right? So this is this kind of philosophy is what we're going to try and build into a general procedure that people can apply to any geometric structure they like, and try and figure what's the general or sort of extremely general uh, family of flows one can choose from, and then worry about the specific choices one could make, regardless of whether this flow is the gradient of anything at all, regardless of whether this corresponds to a variational principle or not. Hmm? Uh, um, Fetishizing about energy functionals should be the job of physicists, not of geometers. That's a sort of underlying thing. We're completely agnostic to the sort of variational underlying narrative, which a flow may or may not inscribe itself into. So we want to address the same type of problem for an arbitrary H structure. And as I told you in the beginning, I'm going to illustrate this philosophy by diving deep into SU2 structures. But let me just real quick refresh what is it I mean by a geometric structure. So indeed, um, we're talking about reductions of the frame bundle of a naive sort of smooth manifold from GL to a particular, well, given a particular symmetry group, which will give a bundle reduction of a principal bundle reduction of the naive frame bundle. And so one can think of these geometric structures, first of all, as reductions in the sense of principal bundle, distributions tangent to principal bundles. We can think of them as sections of the, say, homogeneous fiber bundle associated to a symmetry group H given, right? So where you look at H classes, H equivalence classes of frames, and when such a reduction when such a section is given, then this defines a reduction as in sense before. And there's a third interpretation where you can think of a geometric structure as some sort of tensor on your manifold, or multi-tensor structure, let's say eta. But eta could be a collection of tensors, right? It could be, for instance, a two-form omega, right? It could be an endomorphism J that squares to -1. It could be any sort. It could be a three-form that defines a vector cross product at every point, right? It goes along with the client's taste. The overarching narrative is that such tensor admits an algebraic linear model in some possibly large Rn, some model structure, for instance, J any almost complex structure is pointwise modeled by a choice of frame, which ties in with the previous formulation, right? With the choice of a frame that maps it pointwise to some model tensor at linear algebraic level, which is stabilized by the symmetry group H, the subgroup H you choose. Okay. So, for instance, the metric stabilizing the group stabilizing the metric would be, and so end orientation would be SON, and that reduction from GL to SON is precisely the same as defining Riemannian metric in the problem before. This now encompasses a larger class of structures, many of which I know because I follow your work, are structures of interest to the community in Córdoba. So you may resent, I'm not mentioning here, for instance, context structures or Sazakian structures or whatnot, but they certainly pertain to the same kind of narrative. Sazakian, for instance, could be in odd dimensions and sort of rest of it. Okay, so plenty of examples which are covered by this sort of formulation. And of course, these structures have an associated torsion, which is typically measured. I mean, one way of measure is to look at the parent derivative of the associated metric. All of these are reductions to subgroups of SO n. So in particular, all of these structures determine a compatible Riemannian metric, which gives you a Levi-Civita connection with which you can measure the torsion of these structures. And in all of these notable cases, the torsion-free condition, the absence of torsion, corresponds to special holonomy, as indeed the geometry school in Córdoba very well knows. Kind of famous for it. So choosing the stabilizer group as a subgroup of SON gives you a very strong, very hard in principle geometric PDE, which one could try and solve by flowing an initial condition, which is not so special, towards a more special structure. And if the flow exists for long enough time, then modulo all sorts of analytic considerations and hypotheses, flows are a good device to try and find much more special structures, ultimately holonomy, actual holonomy reductions. So what is the sort of general language one could use to address arbitrary geometric flows? And I should mention, it's not mentioned here, but in the homogeneous setting, colleague Jorge Lauret's work on this business is one of our sort of inspirations, right? When you identify that, in some sense, at least in the homogeneous setting, you don't really care about what specific choice of a symmetry group you're making. You can formulate flows in terms of a bracket flow that's kind of agnostic to what's going on. You're just varying, in some sense, the Lie algebra structure. This led us to think that we should be able to discuss infinitesimal GLN actions on just arbitrary tensors. And from that, we should devise all possible definitions of geometric structures as such, right? We don't want to deform them as naive tensors of the same time. We want to deform them as still reductions of the frame bundle of the same order, okay? So the diamond action is the way we denote the infinitesimal action of an arbitrary endomorphism, say A, in fact, of an arbitrary 2 tensor, if we lower its indices, and it's infinitesimal action in the sense that we're differentiating the pullback action of a big GL on your tensor, right? And then we can pose a very large class of flows. I'm not saying all flows have this form, or conceivable flows, but certainly this is a huge class of flows corresponding to all possible GLN actions on your tensor, uh, would have this general shape, where A is an arbitrary two tensor. Are there any questions so far? Right, so the intuition we derive is that given a original linear model type of structure, which is stabilized by some symmetry group H, we'll deform it sort of directions tangent to its GLN orbit. So it's deformed, it doesn't degenerate, it deforms as a structure of same type. Now, thinking of these two tensors as uh, then given by matrices with two indices, then they can certainly be decomposed into their symmetric and skew symmetric parts. So you're going to recognize here, I'm going to denote endomorphisms quotiented by H as what remains. So seeing as the Lie algebra of the stabilizer H itself, by definition, um, contains your, I mean, tensor in its kernel, right? So I can get rid of the H part and only keep the H perp part among the skew symmetric components. And then for the symmetric component, I can, I'll have to look at it into more detail, right? So typically this degree of freedom, this two tensor, regardless of the context we're discussing, already has some internal structure, and it's really of the form symmetric two tensors plus the complement, the reductive complement of the Lie algebra of your symmetry group, right? So just keep this notation. That's what subscript Lie H means. It's all admissible, all valid, all non-trivial possible deformations. And then we kind of know then where this A has to be as a section of endomorphisms, but what are our actual choices? And here is our sort of I think, most recent contribution to the debate, which is we rediscovered in one of those old notes by Robert Bryant, paragraph we hadn't read with sufficient attention before, which had the key to quantitatively answering this question. Should also mention that in a recent paper on flows of G2 structures, part 2, Spiro Cariglianis and collaborators, in a sense, carry out the sort of program I'm describing here in the specific context of G2. How do they find all possible second order invariants? Well, they essentially differentiate everything with respect to everything, and then look at all possible relations among these guys to try and find a number of linearly independent representatives, which they can then use as building blocks for flows. It's a tremendous work. I mean, it's a 100-page long paper, but we wish to maybe, I mean, lacking their talent for long computational investigations, we tried to get some sort of shortcut, and we found in Bryant a quantitative method to inform essentially how many linear independent representatives we need to find among all possible second order invariants. And those will be sort of independent degrees of freedom if you're going to establish what's the general shape of a family of flows to second order. So what does Bryant tell us to do? With the space of first order invariants, V1, is the space of torsion, right? It's just where torsion lives. It's the space of intrinsic torsion itself. So it's one forms with values in the reductive complement of H. This is well known. That's one of the interpretations of torsion for any given geometric structure. But then the relation you can see here defines the subsequent spaces of kth order invariants implicitly, and so they can be computed in practice. What I mean by implicitly is, if you want to find, for instance, V2, you will expand the right-hand side up to k, I mean, for k equals 2, and you're trying to isolate the copies of that within it so that the complement of those copies is precisely the V2 you're looking for, right? So that this gives you a constructive method to find this in principle vector space. Now, the thing is, this is strictly derived from the representation theory of the group, right? Um, and so it becomes an algebraic inquiry to find the dimension of the space, and therefore, if I go on computing second order invariants, this essentially tells me when I can stop, right? It tells me how many I can expect to be linearly independent. Um, and we find this to be a brilliant insight by Bryant, which people, including Karianis' team, were not considering originally. And Spiro confirmed this to me. He essentially arrived at the same conclusion by working extremely hard, but he did not have Bryant's approach in mind when he set out to do it. So our contribution for the debate can be seen in that way. We suggest that people can use this algebraic approach, and I think the group in Córdoba particularly well equipped to think about the problem in this way, and derive the space of invariants for geometric structures of their choice by a strictly algebraic process, which involves deep understanding of the rep theory of the group, and in some sense, nothing else. Right. The last point I wanted to make is this, right? So as soon as you move on to V2 and to higher order invariants, if one cares for, then you can certainly see that's, I mean, the derivative of torsion has to be there, the Riemann curvature has to be there, but then other second order guys could be there and be related by for instance some constraints, for instance derived from diffeomorphism invariants or whatnot, right? So you are in a situation where if you naively derive second order invariants, you then have to find, sometimes very non-trivially, that they're not independent because they are related by some constraints. Bryant's approach allows us to overcome this problem by telling us exactly what's the expected dimension. So what's total degrees of freedom minus total relations? What is exactly the number of linear independent generators when we would have to look for? Let's look at a few cases. So for the metric itself, well, as I told you before, there are no first order invariants of the metric, since Christoffel symbols are not tensors. And in second order, as we discussed before, you're going to find the scalar, the Ricci, and the Weil. Now, an additional problem is, of course, the issue of multiplicity. We could have several copies of these fellows appearing in the among the reductive complement, right? There's no promise that the irreducible components of the reductive complement do not contain copies, right? You could have isomorphic copies. For instance, if you're varying triples in some sort of hyper situation of where triples are the fundamental object, you do expect triples of copies of the same irreducible representation to appear inside the reductive complement, and this gives you a multiplicity, right? So for each of these components, I have red options, right? But for each of, and therefore the blue components give me multiplicities. And therefore, if I want to find the total number of degrees of freedom I have, I just have to multiply my freedom by my multiplicity. In this case, for instance, we recover the motivating example. Right? There's only one copy of multiples of G, one copy of inside symmetric of Ricci, and those are fundamentally the only two options we have. Now we can play the same game. Let's look at what, let's prove again what Drivedi, Karianis, and Yaniotis proved for G2. Now there are first order invariants for G2. Its torsion has 4 irreducible components, right? There's there's a scalar component, a vector component, a traceless symmetric, 2 symmetric component, and a copy of the Lie algebra itself. its second order invariants now become sort of less funny. Never mind what these additional V's are. None of them is a multiple of the G2 structure itself. So, or I mean, none of them gives me a 3 form that I can use to deform the G2 structure, right? It's kind of like the vial or the uh, Riemann metric problem, okay? So now I have a richer decomposition of my second order invariants, but I don't have multiplicities. The multiplicities are all trivial. Among, I mean, in the sense that the reductive complement the of my symmetry of my stabilizer inside skew-symmetric guys does not contain copies of the same representation. And then, so in this case, a total family of 6 parameters, which is indeed what our colleagues prove, right? So it's given by this this form. The general diamond flow of a G2 structure 3 form is up to second order, has this shape. Are there any questions so far? Can people see where this is going? Okay. My point is that discovering the family of flows is a strictly algebraic problem, which involves algebraic manipulations around the rep theory near your group. So now, for instance, some famous flows like the Laplacian flow with perhaps conspicuous choices of initial condition are particular cases of these of this family. We can do the same for spin 7. I won't repeat myself. Spin 7, although it's I mean, these guys are not the same as G2, but they reproduce the fact of G2, which is there are no multiplicities. So it's a 4-parameter family in this case, right? As found out by Udov himself in an original investigation, and then by Shubham Dwivedi. In fact, they communicate with each other. Beduli and Vizoni, also friends of the South American geometry community, now investigated SU3. And this is the first instance of a genuine multiplicity issue, which pairs with two scalar, two copies of the scalar representation. So then we have to apply multiplicity in order to find a 19-parameter family of SU3 flows to second order. And a side remark is that 7 of the 16 invariants can be found strictly from the curvature. So there's always a role. You have a first stratification of these invariants into those which, in some sense, depend fundamentally on the torsion, and those that only depend on the Riemannian geometry and sort of underlying Riemannian geometry of the compatible metric. Okay, so it's the first way to separate them both, and this allows us to find them explicitly. Now, Udov and I said, great, SU3, 3 is bigger than 2, right? Therefore, SU3 must be harder than SU2. And because we're complete ignorance in representation theory, we made this preposterous assumption, which proved that to be catastrophically wrong. So we thought SU2 is small enough. If we want, it only involves triples of things, so we could use notations like X, Y, Z, and be fantastically happy studying these flows, classify them all, and that would be much simpler. I mean, how bad can it be if SU3 is a 19-parameter family? SU2 can only be easier. And that was a dire mistake because of multiplicities, right? So we, to much of our disgust, not only are these guys, are there problems of multiplicities, but even among all the possible invariants, there are multiples of 3. And if you vary an SU2 structure, you're really varying a triple of objects. And it's maddening to try and determine whether what you see in these multiplicities are three copies of the same information of their, or if they're independent degrees of freedom, right? Is it the same information appearing repeatedly, or this is this a bona fide triple of additional degrees of freedom? It's very confusing. It's a nightmare. Essentially, everything I could expect to be difficult in the study of the original problem happened uh, from the outset once we started digging into SU2. But we pressed on, right? We start something, we might as well just finish it. And um, um, I'll tell you a lot more about SU2. If you want to see how complicated this problem gets as you make groups larger, so you may think, okay, so SU3 is larger, but the problem is simpler. Maybe if the group is very large, is much larger, then the problem always gets simpler, but it's not really the case either. So if from SP1, instead you consider SP2, then you can see that it gets even worse than 72. There's more bits and there's the multiplicities, and for SU2, for instance, SP2 is worse than SP1. So this was somewhat, so SU2 is actually some sort of compromise. It's a naive, it seems innocent as a group. It's not innocent at all, but things can actually be a lot worse. In any event, as opposed to the Riemannian metric, which has no serious first-order invariance, SU2 structures do have first-order invariance. In fact, it's the components of its torsion. You're going to identify the reductive complement of SU2 with the self-dual 2 forms, and essentially the torsion can be expressed by these three degrees of freedom, three vectors, if you want. And that's it, right? They have this shape here. They mobilize the triple of almost complex structures involved. They mobilize the derivatives of the coframe, sorry, the derivative of the, the frame of self-dual 2 forms in this conspicuous way using the hot star associated to the compatible Riemannian metric, okay? Thinking of SU2 as a subgroup of SO4 on a full manifold, okay? Right, so the first order invariance ought to be these ones because, you know, V1 is the space of intrinsic torsion. We can then compute V2, as I mentioned before, in this shape, where we find that we have some divergences of these guys as second order generators. We have these inner products, which are kind of special at the level of 2 forms. So you look at the derivatives of the torsion along the directions of a self-dual forms. And then we have 12 anti-self-dual guys and some other information, okay? Let me hurry up just to show you some of the guys that appear. So the kinds of relations you get, which would correspond to those symmetries I mentioned before, which are kind of constraints, reducing the actual number of identity-independent invariants, they kind of look like this. So for instance, the self-dual vial, although it would naively be a second order invariant, it can be expressed in terms of those inner product guys I mentioned before. So they're not completely independent. Same can be done to find relations with scalar and Ricci, right? So these, if you naively find all possible second order, let's say tentative second order tensor invariants, they will be related by constraints. Focusing on the issue of building flows, we find that any such flow given by an infinitesimal GLN action, a diamond action, actually can be parametrized in terms of these degrees of freedom. And therefore, I'm thinking of an SU2 structure as a triple of 2 forms. Okay, so I'm varying like the symplectic 2 forms, I mean the skew symmetric 2 forms. as a triple, and the coupled system would be given by this shape. Recalling that, allowing for all the possible irreducible components of the reductive complement and um, the actual computation of V2, the implicit computation of V2, this is, corresponds to 72 parameter family of possible choices. The assumption then, I mean, the conceptual premise is that some flows are more natural than others. One way of defining what more natural means is if they arise as gradient flow of some function. But then you'd have to argue that some functionals are more rational, more natural than others. And I find this in general kind of special. So one may think of looking at all possible quadratic functionals. All right, that's being true to the philosophy we're proposing, which is approach all the possible degrees of freedom you have agnostically. So then it's possible to identify 15 quadratic functionals to second order. And therefore, these include, in particular for SO2 structures, the Dirichlet functional and the sort of a Nyanhouse functional, if you want. So the one which is minimized by integrable triple of almost complex structures. If you want to, for instance, carry out a study of how many quadratic functions there are, this is absolutely a viable thing to do. You just have to look at symmetrization of the spaces of torsion, and you'll find out what all possible quadratic expressions are going to be. What I just said may look fancy, but it's completely trivial. Right? How many quadratic things can you build with the first order invariance? Right? That can be algebraically computed. And then you see those which will give you a scalar so that you can integrate against the volume. Right. Let's then consider for SU2 structure a simplification of this form, right? So the Ricci is there. I allow myself a Lie derivative here to perform some sort of de Turck trick, right? I want this to be potentially parabolic. And this is the div T contribution among the skew symmetric variations. So this is symmetric. These two guys are symmetric deformations. And the divs are skew symmetric, right? It's a well-known fact that the symmetric contributions will correspond to deformations of the Riemannian metric associated compatible with your G2 structure, induced by, to your H structure, and the skew symmetric ones will correspond to so-called isometric deformations. Now, from this general shape, we can already find some well-known fellows. So ignoring the Ricci term for a moment, we recover the so-called isometric, or as I would prefer to call it, the harmonic flow, which has already been studied by, myself with a number of collaborators in various contexts, right? So this is the famous div T flow, which is an isometric flow, which we call harmonic because it corresponds to the gradient flow of the Dirichlet energy for fixed metric. You can make a different choice, and then you would have what we've been calling, so you get rid of this Lie derivative and you get what we've been calling the harmonic Ricci flow, which has the promise of having all virtues of the harmonic flow among the isometric directions, but also, in the limit, converge to a Ricci flat metric. And moreover, in the same family, we can fit the general sort of negative gradient flow of the Dirichlet energy, where the metric is also allowed to vary, right? So this also sits in the same sort of very simplified family. And then for that guy, one can prove, making these very particular choices, right? So I had 72 parameter family. let's choose these two parameters and study their parabolicity so that we can compute its symbol and assess if the symbol is invertible in a way as to guarantee that this problem has enough parabolicity to have short time existence. Um, the game here, as you see, is to identify the region in the space of these parameters. So the region among the space that parameterizes my family, where parabolicity is guaranteed. Let's keep this in mind because I want to make a comment at the end. Now, if one sets out to try and prove that short time existence, you'll find that at first glance it is not parabolic, right? A detailed trick is necessary, as in the case of Ricci flow. I don't want to get into too much detail, but we make intervene the same sort of a gravitational tensor trick, which is used for Ricci flow to essentially get a different flow that does exist for a short time, and then pull it back uh, to guarantee existence of our original flow. Let me not explain too much how this goes, but this is exactly the standard procedure uh, to get rid of ambiguity due to diffeomorphism variance in the classical Ricci flow, which we adapt to the diamond action, right? But it's formally the same procedure. And we also have uniqueness using the same types of tricks. If you're familiar with them, you would be able to write the same proof. If you're not familiar with them, that's probably not the best time for me to get into. But you leverage the fact that we already understand the harmonic map, heat flow, and um, uh, from that we conclude that our original flow has to exist uniquely for a short time. So there we go. Interestingly, in this analysis, we find that um, we could freely add some additional second order terms and still get existence because they don't interfere with parabolicity. But um, if you look at the, let's call that the parabolicity region for this family, if you add anything other than these degrees of freedom which are already here, if you add any of the other, say 70 degrees of freedom or 69 degrees of freedom available, they will cause the parabolicity region in some sense to shrink, right? So this harmonic Ricci type of, Lie modified, this harmonic Ricci flow is in some sense more natural in the sense that its parabolicity region is maximal among the freedom you have in choice of the parameters in the extended 72 dimension, right? So in some sense, we discover the harmonic Ricci as nature telling us there's something special or distinct happening for this flow relative to just basically any other flow defined by an infinitesimal G-line action. Further comments. So there's ways to make this Lie derivative less specific, so less idiosyncratic. And obviously, if you want these flows to converge somewhere to more special structures than you began, then it's not enough to study them at the level of second order. The first order terms are also essential, right? First order terms will determine where this flow is expected to stabilize. If it were to exist for a long time, for instance, giving a small initial condition. We do not cover this aspect at all. So we are able, in the case of SU2, but hopefully convince you that this can be done in general. What we do is classify good flows at the level of their short time existence, identifying these parabolicity regions which are amenable to a determined trick to guarantee short time existence. But we make no assumption or exploration or systematic exploration of the first order terms we could add to actually detect useful structures. So this is the freedom to add these first order terms, combining them with our short time. They wouldn't interfere too much with short time existence, right? So there's a whole uh, effort which I believe a community could do, which is to try and see then what interesting first order choices to these flows can lead to more special geometric structures, given that the second order can be chosen in the best possible way. And then obviously, once these flows are understood, there's a whole question about, for instance, their self-similar solutions. So there's a parallel theory of solitons that could be carried out in the light of what I've explained here. None of this is done, not even for SU2, so to speak. I hope I've managed to motivate the harmonic Ricci, sort of slightly modified, Lie modified harmonic Ricci flow as a natural flow to study. It can be modified to first order to the client's taste. It has short time existence and uniqueness, so that's a good thing to begin with. This one is for SU2, but it could be done, the same analysis could be done for just arbitrary symmetry group H. Even the theory of solitons and self-similarity for guys like this on four manifolds is not understood to me, and everything is up for grabs. Even to finish the study of SO2 flows is already a huge task if you consider this plethora of possible directions, and um, how this expresses itself, for instance, on homogeneous spaces, on a sort of almost abelian example construction problems, or the rest of it. All of this is open, and I hope to have intrigued you with the sea of possibilities that's open, but also with the fact that we can do this in a systematic way. And this was for Paolo Piccione. I forgot to delete the last slide. But we should wish him happy birthday anyway.
Great. Thank you, Enrique. I don't know if are there questions or comments?
I think somebody raised a hand.
Um, Maybe it was a clap.
It was a clap, it was a misclap, a mishand. Okay. Right. So yeah, just adding this comment. Precisely, the colleagues in sort of Argentinian school are very good at converting geometric problems into algebraic problems, and then use sort of good knowledge of algebra to classify, construct examples, families of examples, rest of it, right? I think there's a program here of things we could do together, um, which leverage on things. The Cordoba group is probably the best group in the world to do. So I'm open for discussion if you guys, if I can pique your interest. Right? You're certainly better than I am at exploring several of the questions I raised.
Okay. Questions or comments? There in Córdoba, I can see you. Okay, maybe I will stop the recording.